Uh, with 6 minutes to go, this is a voice check. Two minutes, and this is a voice check. Glad to see you all here. Okay, 10 a.m. Welcome to the lecture on Comet Churyumov-Gerasimenko and the Rosetta spacecraft that went there a year ago, more than a year ago. And Rosetta was the first spacecraft to rendezvous with a comet, fly along with it, go into orbit, and send down a lander. And I'm Patio Plasma, also Paul Doherty in real life. I am a physicist and a planetary physicist. I've done research on Mars, starting with the Viking landers on Mars in 1976. So I've been doing this a long time. So, Churyumov-Gerasimenko, also known as 67P, it was the 67th periodic comet discovered, and it is a comet. As it approached the sun, it warmed up and began to have its gases, its ices sublimed into gas, which drove the dust and gas off the surface into a sunlit tail. So we definitely have a comet. It now has an orbital period of 6.4 years. Here you can see we actually sent out the spacecraft, the Rosetta spacecraft, far out into the solar system. The blue circle is, of course, Earth, and the red circle, Mars. And you can see that at its closest, the comet does not get closer to the sun than the Earth. Before 1959, the comet had quite a different orbit and never got this close to the sun. But it was perturbed by Jupiter and put into a new orbit. And so, for the last few orbits of the sun, it's been doing about this motion, and regularly, and so we could actually send a spacecraft out to rendezvous with it. Oops, someone has a microphone on. Okay, so this is the actual size of the comet compared to an American city. It's about 4 kilometers long. That's about 2.5 miles. Which doesn't seem very big until you actually put a picture of it next to a city and you realize if this actually hit the Earth, I see mountains in the background, that's probably not Chicago, that if this actually hit the Earth, it would cause major problems. It's not as big as the dinosaur killer. It's about 1/5 the size, the length, and about and about 1/100th of the volume. Yep, definitely spoil your day. I think that's Denver. So, scientists were surprised. We went there, we put the spacecraft in orbit, and we found the surface temperature of the comet was a nice balmy -68 to -43 Celsius as it came by the orbit of Mars. That's much warmer than we expected. That's the temperature on Earth in the stratosphere. If you're up there in an airplane flying at 35,000 feet and you're reading the temperature gauge on your back of the seat video, you'll find it's about -40 or less Celsius. That doesn't, at -40, it doesn't matter. Celsius and Fahrenheit are the same. And here I am. This image is me standing on the rim of Mount Erebus in Antarctica, where it was a nice balmy -30 Celsius with 30-mile-an-hour winds. My cameraman, who took this picture, took off his face mask for a minute and actually managed to frostbite his nose. So I guess these are balmy temperatures for comets, but they are certainly cold. And indeed, they found out the reason it was warmer than they expected was that the comet was much darker than they expected. And we'll cover that in the next slide. So it's black. It has an albedo, which means how much light does it reflect, of 6%, which is about the same as fresh asphalt. And it's covered with a layer of dark dust. And that dark dust has silicates in it, but also it has organic molecules. Organic molecules are molecules involving carbon. It does not imply that they're made by living things. And now the comet, it's gone by its closest approach to the sun. It's been to perihelion. And with the sublimation of the ice, which is below the surface, there's about a 10 centimeter or 20 centimeter layer of this dark dust. And it gets blown away as the comet comes near the sun and warms up. And that has exposed more ice. So the comet has become a little bit brighter as after it passes the sun. That's right. So the temperature, that's why I mentioned that that temperature was the temperature as it passed the orbit of Mars. It gets warmer as it gets closer to the sun. Right. Oh, that's a nice, Vic notes that Vostok Station in Antarctica right now is minus 93 Fahrenheit, which is colder than the comet. So that, I didn't know that, and that's great. Yeah, the Mount Erebus is not the tallest mountain, that's Mount Vinson, but it's an active volcano with an open, boiling lava lake. And to stand on the rim of a crater and look down at molten lava was really quite an experience. I was actually doing science up there. Okay, so I admit, I have a superpower. It's the same as Tony Stark. Here he is, showing he has his MIT ring, which I have too, the brass rat. And it's a superpower you can get. It's called physics. In physics, we can take data. So we went to the comet and we got data. And I'll give you this, again, something less than this overwhelming amount. But from the data that we know about the comet, if you know physics, I could actually calculate the properties of the comet before they reached Wikipedia. Do-it-yourself science. You'll notice at the bottom center that in June of 2014, it was giving off a third of a liter a second of water into space. The comet has a lot of water ice in it. And then by August, that number had increased to 1,200 liters, 1.2 liters per second. And then as it went by perihelion, that went up to 3 liters a second. So there's quite a bit of water outgassing from the comet. That's per second, kilogram per second of water. Oh yes, I am using voice. So we can do some calculations. If you measure the mass of the comet from the last diagram and the volume of the comet, you come up with the density of the comet. And the density of the comet is about half the density of water, 553 kilograms per meter cubed. The number keeps changing a little bit as we get better and better images of the comet and better measures of the volume. It's about the density of cork, and it floats. And one thing, by having the Rosetta orbit the comet, we can get really good measurements of its gravity. So good, we can look inside the comet using gravity eyes. And one thing they found was that the comet is not low density because it has huge holes in it. There are no giant caverns inside the comet. We can tell that by looking inside of it with gravity. But instead, we see the comet is fluffy because it has complex grains that have stuck together with little bits of airspace in them, kind of like snowflakes, but with silicates and carbon compounds, and ice mixed in there too. It's great. Yes, like Antarctica, where the snow falls, and it's quite fluffy at the surface, only a tenth as dense as water. But then with time, it gets compacted by Earth's gravity. Now, of course, on a comet, we're going to find out gravity is much less, so it's not compacted as much. Okay, and then This number wasn't available. I wanted to know how fast things would fall on the comet. So thanks to Isaac Newton and the law of universal gravitation, I can put in the numbers and find out that the acceleration of gravity on the comet is 300 thousandths, 30 hundred thousandths of the gravity of Earth, 3 times 10 to the minus 5th g, or 3 times 10 to the minus 4th meters per second square. And that means that even without air resistance, because there's no air on the comet, to fall 1 meter, it would take 80 seconds. And so over to the side of the stage, I have a red ball which I'm going to touch. So watch that red ball. And when I touch it, it's going to drop like it would drop on the surface of the comet. It's accelerating. It is falling. So imagine that you dropped a ball out of your hand 1 meter over the comet, and you're watching it fall towards the comet. It's accelerating. Acceleration, it builds up. And let me tell you, building a ball that accelerates this slowly in Second Life took me a few tries because of the mistakes built into the Linden scripting language, but I finally made it. So here it goes. It takes 80 seconds to fall 1 meter. And of course, then it penetrates the 20 centimeters of dust on the surface of the comet. Yes, there's just like different superheroes have different superpowers, different scientists have different superpowers. Chemists can really make a mean martini. That's right. Rock climbing on this comet is going to be so great you'll never need to have a rope. So what this low gravity means is that Muhammad Ali on Comet 67P would weigh the same as a butterfly on Earth. Well, yeah, it's going to take a while to find out which way is up. Just like if you're underwater and spin around underwater and with your eyes closed try to point up. Your body's system for detecting up is not very good, actually. Yeah, so indeed, since you mentioned escape velocity, it's the next slide. So escape velocity on 67P is about half a meter a second, or about 1 mile an hour. And if you were on Earth to jump 1 centimeter high, that would give you escape velocity on this comet. And by the way, it works the other way around. If you drop something from very far away, it will hit the surface at about 1 mile an hour. And that's what the Philae lander did. Oh yeah, in fact, the difficulty is keeping on the comet. Even just taking one step in walking would be enough to launch you away from the comet forever. And depending on, actually, you know, it's interesting. If you jump from any place on an object, you will enter an elliptical orbit of that object, but that elliptical orbit will pass through the launch point. So you will always smash into the object on the other side unless you have a way to give yourself a push once you're at the maximum distance from the comet. Yeah, so in fact it was dropped and it hit the surface at escape velocity, but the bounce, when it bounced, it lost some energy by hitting the dust. So Philae did not have quite enough energy to bounce into orbit, but almost after it bounced. Okay, so let me just talk about orbits. So in fact, Rosetta, we said, is in orbit about this comet. And an average sort of distance that Rosetta orbited the comet at is about 30 kilometers. And that gives an orbital speed of about 3 inches a second, pretty slow. And that gives it an orbital period of 23 days. It would take a long time to go around the comet. So they actually put Rosetta into a triangular orbit. They used their rocket motors to hold it in orbit. They didn't use the gravity of the comet. So they'd fire the motors towards the comet and go in a straight line, and then get to the other side of the comet and fire them again, and then around again, and go in a little triangular powered orbit, because they just didn't have the patience to wait for a nearly month-long orbit to get pictures of the comet. All right, it is a comet. And here you see it in its amazing shape. And of course, as soon as people saw this, they had two theories about how it got this shape. It could have been two comets that stuck together, or it could have been one comet that experienced erosion around its middle. And now, looking at the geomorphology of the two bits of the comet, they really believe that it was two comets that stuck together. And they've been doing a lot of work on that, rather than one comet that evaporated into a strange shape. Oh yeah, a rubber ducky is one of my favorites. And, of course, it rotates. Oh yeah, and it is a comet, and that means that in the sun, as it warms up, the ices inside of it sublime. They turn into gas. And so on the left, you see a regular exposure picture of a pit, a circular pit. Let me turn on my laser here. And I'll point at the pit. There it is. The red laser points at the pit. And then by using a longer, and you can see the scale bar down here. So the pit's 2 football fields would fit across that pit. And then over here at a longer exposure, you see jets of gas and dust coming out of the pit. So many of these pits are not crater pits. They're actually pits made by having the ice underneath sublime and blast out a hole. It's kind of like a gas burping volcano. So in fact, by doing overexposure, we saw something very strange. Normally, we expect the gas and dust to come off the comet from the sunlit side. Oh yeah, the movie Deep Impact, where they had a hole that they could put the bomb inside. Yep, and from the questions online, the evaporating gas does blast off into space, and then we capture it on Rosetta and measure it, and that's how we know what the comet is made of. So this is what's called a trans-Neptunian object. It started out beyond the orbit of Neptune and was disturbed and came into the inner solar system. And in 1959 was its first close approach to the sun. So we're getting to see the pristine composition of a trans-Neptunian object, probably from the Kuiper Belt. And now in the next image, you'll see a jet turn on. Let's see if you can find the jet. Did you see it? I'll repeat that. Let's try it again. Here's the first. There's the second. Oh yeah, so there's not much in the way of metals on this particular comet. Metals you'll find more in asteroids. So if you're going to be a miner, go for asteroids. However, if you want to make rocket fuel, a good rocket fuel involves hydrogen and oxygen. And this comet is made tremendously of water ice. So if you could mine the comet for water ice and then use solar power to split it into hydrogen and oxygen, you've got rocket fuel to then go and mine an asteroid. It's right on the bottom. Yep. So comets don't gain much mass as they lose so much. This comet is thought to have lost meters of surface on its passage by the sun, on the sunny side when it got to perihelion. So that's a lot of loss to make up for with impacts from dust. And so the jet that turned on actually was in the shady side. And that was a real surprise. We always thought that the jets would come from the hottest parts. But this shady side here actually was in the sunlight as the comet rotated. And so it was warm in the past. And so that jet turned on. I guess the pressure built up, and finally there was an eruption. And that was a real surprise. Planetary physicists are often surprised. You bet. The change, so the outgassing and the change in shape changed the rotation. And we'll get to that. I'm coming to rotation soon, and I'll give you the details. In fact, it changes it a lot. One of the things they have on the Rosetta are several 1 centimeter square patches that collect dust grains. The comet actually shoots out dust grains, and they actually name these dust grains, as you can see in this image, so they can talk about them. And they can use, they can then study what the dust grains are made of, and they're finding silicates and carbon compounds. So it's really a nice way to pick up. And then here is the latest close-up of the dust grains. And you can see they've really splattered on the surface as they hit the collecting plate. Picture a fractal made of dust, where just particles have stuck together, come together and stick together at random, and then this dust particle smashes into a plate on the spacecraft. And one of the stories here is that we're going to find out later about the lander Philae. And in order to contact Philae, they wanted to bring Rosetta close to the comet. But the comet was getting close to the sun, and it was spitting out more and more and more dust. And so as they went close to the comet to try to pick up the radio signals from the Philae lander, the dust surrounding Rosetta reflected so much sunlight that the star sensors on Rosetta looks at the stars and uses the stars to maintain its orientation in space. The star sensors lost track of the stars, and Rosetta started to tumble out of control. But luckily, the programmers thought about that. And so they had Rosetta plan to go close over the comet, but then go far away on the other side. And when it got farther away from the comet on the other side, it got clear of the dust, the sensors recovered, it stabilized itself, but they then moved the spacecraft away from the comet, going as far as 1,000 kilometers away recently, and that'll be the last image I show you. But now, having passed perihelion, the closest point to the sun, they're moving the spacecraft back closer, really close. And at the end of the mission, they're going to land Rosetta on the surface of the comet. Yes, so in fact, they've named some of the features on the comet for members of the Rosetta science team that passed away during the course of the mission. They named them after dead people, and they won't say who they named the dust grains after. Land as in crash slowly. They're going to try to land it on the comet so slowly it survives, and they can continue to get data. Okay, so Comet 67P, it has here's some data. It rotates about the same speed as the hour hand of a clock. And here's the deal. On its last pass around the sun, 6.5 years ago, it was rotating once in 12.6 7 hours. And by outgassing, as it went around the sun that time, the rotation sped up. So now it rotates once in 12.4 hours. So we've actually seen the rotation change in one orbit. Yeah, that's right. We know from the Hitchhiker's Guide to the Galaxy that the way that you fly is that you trip and get distracted, so you miss the surface. So orbiting is falling while missing the surface, and landing is controlled crash. Perhaps like the sheep in Monty Python when they jump out of trees, it plummets. But under the gravity of Churyumov-Gerasimenko, it plummets slowly. So the polar axis runs through the neck of the comet. That gives it a northern hemisphere and a southern hemisphere. It gives it an Arctic circle where the sun does not rise, and it gives it an Antarctic circle where the sun doesn't rise. And the southern hemisphere is the one that's in the sun when the comet is closest to the sun. And that's what loses many meters of ice on each passage around the sun. And the northern hemisphere is the one that's in the sun for the rest of the orbit. So if you give me just a minute here, my friend Gitana made for me a model of the comet. Let's see if I can res it here. There it is. So over your heads, there is a model of the comet. And it is rotating about the correct axis. So what we've done is, on this one, if you look around the back, you'll see that the back is just flat. And that's because the back of the comet, when this model was made, was in darkness. It was the southern hemisphere. It never got in sun. And so all we knew of was the northern hemisphere. Of course, saying hemisphere when something that's shaped like a duck is stretching things, but I'm going to call it the hemisphere. The hemi-duck, perhaps? That's right. It's the nickname for the comet is 67P, as in the 67th periodic comet discovered. I'll let it go around once here so you can really see it. And while that's happening, and while you're watching that, I will bring back another comet ball. If any of you would like, you can. I believe that you can take a copy of that comet ball. Maybe I forgot to make it. You can try to take a copy of it. If you touch it, it will fall. Yeah, so, you know, when I was giving this lecture in real life at the Exploratorium, or a lecture like it, I actually brought the visitors into Second Life so I could show them this model. There are things you can do in the virtual world you just can't do in real life. The dropping ball, that's a great thing to do. It's really hard to make a ball drop at that slow rate on Earth. Well, I'll remove the comet. There it goes. Okay, back to the lecture. Yeah, you know, science education in virtual worlds is really great. I'm looking forward to the future of virtual worlds. And all of us that are here will be way ahead of the crowd when it happens. Okay, so in fact, here are a few images of the comet actually rotating, a little more detailed. Yeah, we're here, but the rest of the world isn't yet. But they're beginning to bring out browser-based virtual worlds. The first one just came around, and when those happen, and people can just do things in 3 dimensions, animated, and virtual reality goggles in a browser, then this will take off. Okay, that means there's a pole star. That axis, the North Pole axis, actually, or maybe the South Pole axis, it points to Alpha Camelopardalis. It's a magnitude 4. You can see it with naked eye. Star. Oh yeah, it's a Northern Hemisphere one. I can see Cassiopeia and the Ursa Major and Ursa Minor in there. It's actually reasonably close to our pole star. Oh, that's right. Yay, yay. Vic just mentioned that the comet was going an order of magnitude faster than a bullet when Rosetta caught up with it. So, yeah, catch a speeding bullet. The engineers at ESA who run this mission are doing a great job. Okay, so in line with Game of Thrones, winter is coming. The seasons on this comet, it's summer for 5.6 years on the side we first saw, followed by winter for 10 months on that side as it whips around the sun. And the side that was in darkness has summer for 10 months near the sun and loses tens of meters by sublimation. Take that, Game of Thrones. We now have a complete geologic map of the comet, and it's much more complicated than we ever thought. Yeah, so if you take count that it's 4,000 meters in length, and it loses 10 meters every pass every 6 years, it's going to take a while before it's all gone. And the names on this diagram, they're named after Egyptian gods. And I'll point out to you one you're going to see later. Imhotep, over here on the right, is one of the important areas. Bes and Geb have just recently come into view because they're in the southern hemisphere here. It's great. A lot of this information I'm bringing to you from both the American Geophysical Union meeting in San Francisco last December and the Lunar and Planetary Institute conference that happened just last month. And so as a planetary scientist, I get to go to those conferences or at least view them online and then bring the information to you. And I really love the posters, to walk down the aisles in the poster sessions and see these great images. Yes, so the regions here are named for their textures. Like on Imhotep, it's very smooth textured. It's like it's covered with a layer of dust, deep dust. I'm going to show you, the next few slides I will show you are close-ups. Yeah, you want that happy god. So here we go. And this is how those regions map onto the comet. So you know that flat view just doesn't do it justice. And you can see here that up here that this one is kind of a crater-like, and here's Imhotep over here at the base of the butt of the duck, and some of the different ones. Well, now let's take a tour and show you why they have different geologic names. So here is the North Pole, right down in here. And this is called the neck of the duck. And look at the striations on this cliff face. I mean, the rock climber in me wants to actually climb up this wonderful grooved face. And of course, one finger pull-ups are nothing on this comet, and you don't need a rope because a fall won't hurt you. Oh yeah, I bet, Chantal. But this whole lecture will be available if people write to me I'll give you my email address in if you want it. But what will happen is, of course, Science Circle will post the slides online afterwards, and Q, when he gets back from India in early May, will put up the actual lecture. And here's an interesting thing. In the neck, there is a crack. And some scientists have modeled what that crack means. And it turns out we know that the comet speeds up and slows down its rotation due to outgassing. And they calculated that to open a crack this big in this orientation in the neck of the comet would have to spin faster than once every 9 hours. And right now it's spinning once every 12 hours. And they calculated that it's quite reasonable for the outgassing to speed it up that much. And they actually went further, and they found out that if it rotated once in 7 hours, it would fission into 2 comets once again, but without escape velocity. And then eventually the comets would come back together and dock together as a new double comet in a totally different orientation. And that's one of the ways they know that the 2 bodies are different. They look at the layering, the sedimentary layers in the different bodies. And in fact, as Bergeron mentions, there's a possibility that comets like this have come apart and come together many times during their orbiting of the sun. Well, so the outgassing from one orbit near the sun changed the period by 20 minutes or so. They went from 12.7 to 12.4 hours. So it's going to take a long time to actually speed it up. And of course, it's a random walk. So the outgassing could just as easily slow it down. So it takes a while. Like lovers. Yeah, I like that. Oh, yeah. So given the fact that it's got, there have been hypotheses that there are the organic molecules might be the result of organic life, but the Rosetta spacecraft does not have the ability to detect the presence of life. So all we can do is say that there are organic molecules, simple organic molecules. So I'm going to show you 3 more slides, and I wanted to show you where they were taken on the... Bergeron just made a nice comment, says P67A and P67B sitting in a tree. Nice. Oh, yeah, right. Yeah, I am a climber. Okay, so so I'm going to show you the fist, the pit, and the cliff. So this is where they are on the comet, and here they come. So here is the layered fist, and you can see that it looks like there might be hard layers running side to side with softer layers in between. And this gives us, for geologists, seeing layers is like, whoa, they're layers. And we really like to see layers. We don't understand how they're made, but it's nice to see layers. And here we have the cliff up here on the skyline, this thin wall sticking out into space. And one interesting thing about this comet, there are boulders everywhere, just giant boulders. The comet is crumbling into big pieces that slide downhill, whichever way down is on this complex-shaped object. That's right. You know, on a sphere, it's easy to tell which way to fall, but on a comet this shape, imagine the calculations those poor stones have to do to integrate the mass of the object and find out which way down is. I don't want to do that. Now here's a real puzzle. Near the neck, over here on the right, you'll see things that look like sand dunes in the dust. Now, and also notice these great cracks here. There might be layers with cracks in between them. So the big dust fields, but it's in a vacuum. We have no idea how you can make sand dunes in a vacuum. And it's even worse than that. Here's a close-up. Here are the very same sand dunes you saw before. They really look like sand dunes. And over here, we have the tails behind objects. This is what happens in the Arctic and the Antarctic when snow is blowing in the wind. And the snow gets deposited. But it's a vacuum. Now, there are dust plumes ejected from this comet. There's dust going around it all the time. We have a lot to learn about the physics of blowing dust in a vacuum. Yeah, so some of the answers in the audience, outgassing expanding in clouds along the surface, that's probably going to be the answer. And the interaction with the solar wind. So there's lots, as I said, the temperature changes a lot on this comet when it's near the sun and far from the sun, many tens of degrees Celsius. And because it's made of ice, which expands and contracts, that makes fractures, it makes erosion. And you can see here the giant avalanches covered with boulders as the cliffs disintegrate and fall. So we really can look at these boulder fields and learn about the comet. Yeah, whenever we look at a new body, we find out things we never expected. And here's another big avalanche over here. You can see it falling down from the cliff and spreading out over the dust. And another one over here. So geologists just love to look at these high-res images. Yeah, you could probably pick up a boulder. Not the big ones. These big ones here are tens of meters in diameter. And just a nice picture. But over here, you can see why I showed it to you. This entire cliff, with freeze-thaw, is crumbling into boulders. And of course, the boulders will then evaporate more quickly. Yeah, evidently, but so the question is, why isn't there a shroud of dust around the comet all the time? And the answer is that almost everything has escape velocity. And if it doesn't have escape velocity, within a day or two, it falls back to the surface. Yeah, so a lot of the photos you saw are single images. This one was put together. When the spacecraft is close to the comet, it has to take multiple images. Even its wide-angle camera can't take in the full comet. So they make mosaics for when they're really, really close. And recently, on the left-hand images in this picture, it's in the infrared. They have an infrared camera, and it shows temperatures. And the arrow up here is pointing to a white band, which is cold. It's very low emission. And over here, we see that this is a visible light image of the same feature. And these are cliffs that the infrared and the visible together tell us you're seeing water ice. So this tells us that for sure there's water ice inside the comet. And this right-hand image over here, both images actually, that is that region called Imhotep, a flat plain. And of course, that water ice is subliming. So some weird features on the comet. Look at this pit, rimmed pit. It's got a really thin rim. Climbers often love to run along rims. Just going along the rim here would be great. I love the shadow. It really helps bring out how thin this rim on this pit is. Oh yeah, there's 13 gigatons of ice on this comet. But if it crashed into the moon, a lot of it would be lost. Maybe just harvest it in place. So there are pits all over. Look at these pits here. We're used to looking for craters, but these look really strange. And in fact, some of them are full of stuff. Some are empty, some are full. And that's kind of weird. So let me show you why they might be full. Yeah. So, in fact, maybe a crater, then the impact crater compresses the ice around it, changing it to a denser structure, which then sublimes more slowly than the fractal fluffy ice. And so this could be the result of cometary erosion on an impact crater. Yeah, and so Vic has mentioned about as we look at the water vapor that comes off the comet, which we have, and we find out that the comet has 3 times more deuterium in water, H2O, or DHO, than on Earth. This answered one of the great questions that we had when going to the comet, and that is, did the water on Earth come from comets like Comet 67P, or did it come from rocks that were melted and outgassed in volcanoes on the Earth? And because the deuterium in the comets like 67P is so much more prevalent, it now tells us that the water on Earth did not come from trans-Neptunian comets if they're all like 67P. And since we only have one example, that might be a bit premature. Oh, yeah. And it's always great when Paradox is here. He knows his science fiction. Here's a pit. So looking inside the pit, if you look inside of this, actually in here with my laser pointer, you'll see a funny structure. And down on the bottom, you'll see the scale bar, 40 meters. So these are several meter across spheres. The inside of the comet seems to be made of a pile of multiple meter in diameter spheres of ice. The people who discovered this image named them dragon's eggs, which I think is a great name, but a bit misleading. We don't know what they are or why they formed. And it may be that the comet was actually made from spheres of ice that grew to a meter or few in diameter and then stuck together out in space, and that's how comets were made. Oh yeah, Frederick Pohl is great. He's a great science fiction writer. Knew his science. So here's one thing. So this is a pit, and there's a flow structure coming out of it. This is a flow that comes out of that pit. So it may be that the pits allow volatiles to escape from inside the comet, bringing dust and materials with them that flows out over the surface of the comet. And that may be why some of the pits get filled up on the inside with dust. Yeah, the comet vomit. Indeed, it's barfing. So here's Imhotep, right over here. This is the plain known as Imhotep. And you can see how the geologists might name this region a different geologic region than this one over here, which looks like bare surface, fractured. And here's Imhotep. Well, let me show you how Imhotep changes with time. So here it is, Imhotep close up. Some of the biggest boulders on the surface, 75 meters high, 300 feet high. Be a great climbing challenge. I couldn't lift these with one hand. They're too big. And here's Imhotep over time. And you can see that in the upper left picture, in May, this is the surface of Imhotep, and then watch the red and yellow arrows as time progresses. Here's June, here's July, and you can see that the subsurface is subliming, blowing away the dust, making new pits. We're by orbiting this comet for months, we're able to watch the comet change as it passes around the sun. There are sort of color pictures, but the comet color is gray, dark gray, light gray, reddish gray. The color pictures are actually made up using some infrared images as well, which is the image that a snake would get. Right there. So, yep, Vic mentions maybe these are color photos. Yeah, it turns out water ice, silicates, and carbon compounds tend to be gray. Now, the first image of the dark side of the comet. A misnomer, just like the dark side of the moon, but so this is the south pole of the comet. The rotation axis comes out over here in the neck, and you can see that this portion of the comet looks really different than the north side. Look at the layering in the neck. I'll give you a close-up soon. So it's great that we were able to finally see the structure of the comet on the far side. Now we've got the complete geologic map of the comet. Yeah, the orbital year is 6.4 years, 6.45 years. They sometimes round it up to 6.5. So 6.45 years. Yeah, they're only colored arrows on a comet after the graffiti artists have gone there. Those geologist graffiti artists, they all put arrows anywhere. And here's the close-up I promised you. So in this one, you can actually look at the layering, which is visible on the south pole of the comet, and compare the structure on one comet object with the other, and see the layering really looks different from one pole, one blob to the other. And the comet has fractures. Geologists love fractures just as much as they love layers. And so here you can see some beautiful fractures at nearly right angles. This face here in the shade is nicely fractured. Up here, this one, fractures all over it, fractures all over this one. And those fractures come about probably from the freeze-thaw. But of course, when deep underneath the comet, it warms up and the gases are pressing out on the surface. You can make fractures. And in fact, as was mentioned in the comments, those fractures are probably a good place to look for any organic life forms. Fracking comets. I like that comment from Dolly. Okay, so now for the story of how Rosetta gave birth to Philae the lander. So here's Philae, ready to come out. And so Rosetta was in orbit, and Springs launched Philae away from Rosetta. What they did, actually, Rosetta was moving along in orbit, and they pushed Philae out with just enough speed so that it was stationary relative to the comet. It was just stopped in space. So what did it do? It fell towards the comet. And inside of Philae, there's a reaction wheel. It was spinning around, maintaining its orientation correct so it would fall to the comet. And here's what it was supposed to do. It's supposed to land and fire 2 harpoons into the surface. It had a little rocket motor on the top to push it down, and it had 3 legs that had ice augers on them that would bore into the surface and hold it in place. The problem was the rocket motor failed, the harpoons did not engage the surface, and it never stayed down long enough for the ice screws to work. So although it fell right on target, it bounced and was not able to anchor itself. Oh, yeah, it's nice photo. It's a fake. So here's where they're going. They're going to go to a place called Aglykia, which is the name of an island in the Nile where the Rosetta Stone was found. And that's where we're headed. It did survive. That was amazing. It survived the bouncing. So here's the close-up. Again, we usually try to land on dull places so that we survive. But they didn't pick the super dull place. They were willing to chance it a little bit. And so we'll see how they did. It dropped from 30 kilometers altitude. the acceleration, the drop height. You can say the impact speed was 1 meter a second, and it's about the mass of a 220-pound person, 100 kilogram, and traveling 2 miles an hour. So you'd notice that if it hit you, and it bounced. This was what they had to do to drop the comet, to drop Philae. This is the orbits that they programmed in around the comet in order to drop Philae. And so here's where they drop it, and here's where it is after it hits, so they can watch the impact. And here's a picture. My baby! Rosetta takes a picture of its baby heading to the surface. Yeah, man, those engineers at ESA, they're good. Almost as good as JPL, where I worked. Anyway, and this is the picture from Philae as it's heading down towards its landing. Really nice. They had a nice belly cam just to show pictures on the way down. And here it is, just before hitting, just a couple meters up. We're seeing rocks here that are just centimeters in size. And we got images from the spacecraft that show, here it is, that's where it hit first. Here it is during the course of its bounce. So it bounced off the surface, and this first bounce that you're seeing here it went from about half an hour to make that bounce. Then it hit the rim of a crater and deflected again and made another bounce over to here. And then it bounced again. And this went on for 2 hours, and it traveled a kilometer across the surface before it finally came to rest, crash landing. Oh yeah, I really love the images on this mission. So here's the profile. Here it is dropping from the spacecraft right here, hits the surface, bounces, hits the rim of a crater, bounces again a little higher, just barely doesn't reach escape velocity, hits, bounces again into unknown territory. They weren't able to follow it after this, but it bounced at least one more time. And where it landed, nobody knows. We don't have a picture of it yet. This is where it hit first, right over here in the X. This is where we think it ended up, but it's in the shade. We haven't been able to photograph it yet. They're going to lower the altitude of Rosetta as it orbits and try to get a high-res picture to find out where the orbiter landed. And here's the picture sent up from Philae of the cliff it landed against. Down here we see part of the lander. Real nice close-up of the rock, which is, of course, made from water ice. That's right. Vic says some space tourist is going to take a selfie standing next to Rosetta. I bet they will, or standing next to Philae. I'm sorry, I'm going to go just a couple minutes over. I'm almost done. And here's several. These are 4 images. They had multiple cameras taking photos in different directions from the landing of the spacecraft. You can see it's in the shade. Because it was in the shade, its solar panels couldn't work to recharge its batteries. They lasted over 70 hours, 3 days, and they did 80% of their science measurements, but they'd really like to know where it is so they can make sense of the science measurements. Yeah, they have no idea why the harpoons didn't deploy. Really, really good questions for the engineering team. And here's my bet. I love this meme on the internet, which is what really happened to Philae. I kind of like this. And what the ESA says is that Philae just entered eternal hibernation. And I translate that into, it's dead. Yeah, I really like the sense of humor on some of these. So I'm going to end with just 3 more images. Tremors! I love that movie. Tremors 2. Tremors on the comet. So this actually down here, this is the shadow of Rosetta on a close approach to the comet. And so that, of course, if you were standing in there, you would be in a partial solar eclipse. The spacecraft isn't big enough to actually make a total solar eclipse. However, it can take, the comet itself can do a total solar eclipse. So this should be the last image. Solar eclipse viewed from Rosetta. It moved away from the comet because of all that dust near perihelion. And so we see that it's jetting away, changing its rotation, heading back out into the cold of space. It'll be back in 6.5 years. And next, we plan in this December to land Rosetta spacecraft itself with its giant solar panels on the surface of the comet. And we hope that it will keep operating and we can just ride the comet like riding the bomb in yeah, How I Learned to Stop Worrying and Love the Bomb, the movie. It's Dr. Strangelove. Yes, thanks. I'm drawing a blank on Dr. Strangelove. But you can see the comet has a saddle, and Rosetta can land on that saddle and ride the comet out into space. And I think that's a good place to end the lecture. And I'll stay. That's it. I'll stay around for questions, and I hope you had fun on my tour of the comet. Oh, thanks, Moon Snail. Yeah, I learned to use this style in Second Life. And very often, when I'm training my postdocs, I'll have a postdoc with me reading the questions from the audience and answering them in text. I don't have a postdoc at the moment. And that way they can learn how to do this style. Right now I have to actually watch the postings myself, and I have to look at IMs as well. So looking at instant messages, looking at the chat, it's a great way to teach because people who are shy can send an IM and they don't have to worry about what people will think about their question. And it allows me to go ahead and lecture and you to be quiet and yet ask questions. I really love virtual worlds as a place to do science education. Oh, thanks. Yeah, so my friend Gitana made the model. And it's really something to make a mesh version of the comet and then put the texture on it. Oh, thanks, Vic. I love that image that you posted. Okay, I guess Gitana now has her assignment. Yeah, so if you'd like a copy of the comet, you can write to me and I'll ask Gitana if she's willing to share a copy with you. And so yeah, and of course the geologist must paint the colored arrows when they're doing their studies. Yeah, actually, we probably could have Rosetta orbiting the comet. Anyway, so Science Circle is a wonderful place to give presentations. They record these presentations on videos to be seen later. They'll come out after May 5th. They also distribute my PowerPoint. Actually, I use a Keynote, but then I translate it into JPEGs, a series of JPEGs, so that anyone that's out there as a teacher and could use some of these images, you can get them from the Science Circle. Watch the Science Circle. Maybe one of the Science Circle people in chat could post the HTML address for the Science Circle website where you can get access to these images. And there are other great talks. The speakers here are all excellent speakers. I come to every one that I can. because I can learn. There are people who have been giving lectures in Second Life for a long time and have developed some great style, and we can always learn from each other. Yeah, Vic has posted sciencecircle.org/?page space ID equals 88 is the index for the other lectures. Indeed, Leslie mentions that science is better with mermaids. And earlier on, she told me that mermaids actually eat ducks. So I was worried for my comet when it arrived. But looking at Leslie's wonderful shape, I suspect she doesn't eat things as big as ducks as big as the comet. Oh, yes. So I did a previous lecture a couple weeks ago on the latest discoveries from Pluto. The Lunar and Planetary Institute had its planetary conference, and like a day after the planetary conference, I was able to give the latest information on Pluto as a lecture in Second Life. Just so amazing that we can reach people all over the world, and thank you for those of you who are watching this in the middle of the night, because of virtual worlds. And to me, that's powerful and amazing. And we also did the total solar eclipse from the Exploratorium. And if you hang around for a minute, I might be able to go out and get the link to the total solar eclipse. Takes a while. Yes, thanks, Jess. I appreciate it. I've done the same, however. Not quite the middle of the night, but I'm a mountain climber, and mountain climbers sometimes have to get up at midnight in order to climb the mountain before it melts. I did that for Cotopaxi. Let's see. I'm still going out and getting the address so you can watch some of the wonderful images from the eclipse. Let it load there. Anyway, so it was a wonderful mission to a comet. The spacecraft worked great. They really got some good data. They discovered that the comet dust repels the solar magnetic field. There's a magnetic field bubble around the comet because of the interaction of the solar plasma with the dust, which ionizes the dust, and the ionized dust repels the plasma. They didn't expect that. And the comet itself has a weak magnetic field. They didn't expect that. But the bouncing of Philae across the surface gave them a chance to measure the magnetic field at different places on the comet, which was amazing. Oh yeah, it's great to watch sunrise from the summits of mountains. I had to do that in Cotopaxi, and it was amazing. And the organic molecules are not all the way up to amino acids yet, Vic. They're the predecessor molecules that could be made into amino acids. They were looking for the predecessors to ribose, a sugar that is the R in RNA. So that's right. They really did a good job after the bounce. Okay, let me see if I can have now downloaded the website for the eclipse. It's still coming up. There we go. So here is the place to go and see many videos of the eclipse. There's a 5-minute highlight reel of just totality. There's a 3-hour version of the entire eclipse. There's a 1-hour version in English and Spanish. The Exploratorium won a Best of the Web award for our total coverage of that total solar eclipse. And you can, I'm glad these aren't your last hours, Jess. And you can actually see my real-life avatar, Paul Doherty, on video doing some of the presentations. That's good. Well, in fact, for those of you that stayed, let's see. Here's one with a nice website that actually you can, on that website they have a 3D model up to date of the comet that you can rotate around and look at. Okay, I don't want a mermaid to dry out. Not pretty. Okay, so I'll have to ask Rob Knopf. He's another great lecturer here, and he made the revision of this slide screen. And Troy McLuhan as well. I'll have to ask if they could make it so that anyone in Science Circle can actually advance through the slides. And was anyone able to actually get I should probably set this ball for sale for $0. Hold on a minute here. Let's see. For sale? Price? 0. Okay, so the ball that drops with the speed of the comet is now, if you couldn't get it earlier, it's now for sale for 0. It was really fun trying to make it. First of all, I tried to make it physical, and the round-off errors in Linden's scripting language wouldn't let the ball drop as slowly as it drops on the comet. So I had to actually program a non-physical object, and I had to actually, for 10 years as a physics professor, I taught a class in how to solve physics problems on a computer using finite difference calculus. And so I had to actually write my own code for the physics of dropping the ball and encode it in Linden's scripting language in order to get that ball to drop. And it's really good when you've taught a class for 10 years to finally have a use for it 40 years later. Well, actually, it's only 30 years since the end of the class, I guess. Yeah, right. I like Ding's comment. Yep. At the moment, that's the slowest accelerating thing in Second Life. Yeah, so I have to think about my next lecture. Of course, I will always keep you up to date on the latest in planetary physics, but I have a lot of lectures I've prepared through the years, and I was looking forward to, if people are interested, I have a really lecture I like a lot on lightning. Lightning is something that mountain climbers really want to learn about, and physics professors too. So maybe in one of the open slots coming up, I'll be able to squeeze in a talk on lightning. What I have to do first is to be able to make a lightning bolt in Second Life, and that will take me more than a couple hours to make, with the step leader and the return stroke and everything. Oh, so I'm actually the wow, that's wild. Um, so I actually am the senior scientist at the Exploratorium in San Francisco, and before that I was a tenured professor of physics at Oakland University in Rochester, Michigan, and that's when I worked at JPL on the Viking lander mission on Mars. Um, and oh, that's right. Oh, that's right. I will actually have to ask Sarah about because it's some pretty interesting scripting on the step leader. You have to have each path in the lightning bolt res the next path in position, stepping down towards the surface of the Earth, and then illuminating them all in opposite order. Um, so Aaron, that was a great little flash there. So thank you. Anyway, other questions? Yeah, the I work at the Exploratorium. I've worked there for 30 years. I really love it there. And um, the Exploratorium was the first science museum in Second Life. We have a sim. So you just look up Exploratorium and visit our sim that is full of hands-on science activities. And we also have another sim called Splo. And oh, thanks for putting those down. Yes, and at the welcome area when you arrive, I have a gravitational wave. It turns out I was ready to give the gravitational wave lecture, and then Rob Knopf did a fantastic job. So I gave him my animated 3D gravity wave model. Yes, and so it turns out I made Splo first, and it's a parody of hands-on science museums. It is much more humor. The Exploratorium is fun. The Exploratorium makes fun of fun. The Splo makes fun of fun. So go check out our warped sense of humor in Splo. Yes, in the one of the places you can. Oh, okay. Let's see if I can give you the Splo URL. Maybe I have one. Just a minute. Just a minute. I'm working on getting the Splo URL. Oops. I don't have one available right now. Drat. But just search for Splo. You'll find it. Okay, probably time for me to sign off. So thank you all for coming. A great crowd tonight, and have fun studying comets. Right. Splo is adjacent to the Exploratorium. Thanks, Science Circle. Thank you all. See you next time for lightning, I hope. I'm going to drop the ball one last time. So here it goes. Oops. Oh, it doesn't work now because I sold it. Okay, so let me remove that. So you have to remove the for sale. Too bad. All right, didn't realize that. Here we go. Dropping the ball. Oh, Giuseppe Longo is a great lecturer. Drat. I'm actually teaching a class, so I'll have to catch it, Giuseppe on video. Remember, if you want a copy of the comet, ask me. Yeah, New Year's Eve on the comet. Well, in the northern hemisphere, perihelion is when they'd reset the clocks to 0. As it sinks into the dust on the stage. By the way, the ball does die when you drop it, so it doesn't clutter up the space. Okay, I'm off.